Hello and welcome to 3.4 Arithmetic Sequences. We are going to be using pages 64 and 65 in your student companion, so follow along and let's learn. All right, here is a ordered list. So we're going to go ahead and understand what is an arithmetic sequence. So right now we're going to take a lot of notes, okay? A sequence, I would say there's certain words we don't have to write down if you already know what they are. For example, if you know what a sequence is, you don't have to write it down. But if you don't, a sequence is an ordered list of numbers that often forms a pattern. Each term or each number in this sequence is called a term of the sequence. I would say to write that down. And in an arithmetic sequence, the difference between any two consecutive terms is a constant called the common difference. So I would definitely write down this part here down to here in your notes. Okay, so an arithmetic sequence is just a sequence of numbers. So here we have our sequence of numbers right here. And as long as the difference between each of these numbers is the same thing when I subtract them, so in this case, they all are 13, okay? If there's a common difference, it's an arithmetic sequence. So you might be asking yourself, okay, so why are we learning about sequences when we've been learning about functions this whole time? So you can think of a sequence as a function where the domain is the natural numbers and the range is the terms of the sequence. So here's an example. Here's a sequence right here. Okay, these are going to be your these are your terms of the sequence, so this is your range. Okay, and then your natural numbers, that's your difference, your common difference. So here it says let n equal the term number in the sequence. So a of n is the value of the nth term in the sequence. So a of 1 is 26, that's the first term in the sequence here. A of 2 is 39, that's the second term in the sequence. A of 3 would be the third term in the sequence, 52. So that's kind of how they're related. Okay. We're going to learn a little bit about how you can represent these sequences, and we're going to use something called subscript notation. Subscript notation is commonly used to describe sequences. So if you don't know what a subscript is, it's written in English, or we use it in English, like ELA as well, but it's basically a little letter or number that is below your original number. So think of exponents are superscripts, they're above, subscripts are below, okay? So A with a little 2 is 39, that's going to mean the second term is 39. So this little subscript is how I'm going to say that the second term in my sequence is 39. When we are writing these, you can use function notation or subscript notation to represent sequences. You'll see both. Okay, so what you are going to go ahead and do is tell me if a of n is the value of the nth term of this sequence right here. Is the domain of the function continuous or discrete? And hopefully you remember what those two words mean. Continuous means if I were to graph it, I would end up graphing my points and drawing a line through all of them because all of the values between those points work. A discrete graph or a discrete function is individual points. Okay, it only works for those individual points, and the numbers between those points do not work. Okay, this lesson is full of vocabulary and note-taking because it's a lot of stuff that you haven't learned before. So here we're going to go ahead and write down the definition of recursive. So with arithmetic functions, you can write either recursive formulas or you can write explicit formulas. The recursive formula is as follows. In mathematics, recursive means to repeat a process over and over again, using the output of each step as the input of the next. A recursive formula relates each term of a sequence to the previous term, and it's composed of an initial value and a rule for generating the sequence. So you'll notice that here, we're going to use A with a subscript of 1 to represent the first term of the sequence. If I'm trying to find any other term in the sequence, an nth term of the sequence, it could be the 10th, it could be the 100th. I'm going to go ahead and say that a n minus 1, that's the previous term, so whatever number I have, take away 1, plus the difference, that common difference, right? So to get from one number to the next, I'm going to add the difference between those numbers. So I'm taking the previous number, I'm adding the difference, and that's going to equal the number I'm looking for. And the way that we use this formula is you would find the next term in consecutive order, and then you would use that answer to find the next term in the sequence in consecutive order, and then you'd use that number to find the next one. So it's like this repeated formula that we use over and over again to find the pattern of a sequence. Okay, so let's show you what that looks like. So we're going to write the recursive formula for the height above the ground of the nth step of the pyramid shown. So if every step is 26 centimeters tall, then we know that the very first step is going to be 26 centimeters tall. So that's going to be our first term, our A1. The next term is going to be the previous term, which ended up was the term take away 1 plus 26. Since every step is 26 centimeters, it's the same height, we're just going to keep adding 26 every time we want the next step. So this formula right here gives us the height above the ground of the nth step, okay, with the first term being 26. So I could find the height of the 100th step here by just replacing n with 100 and then calculating this formula. So let's practice. Okay, so we're actually going to find the step here of the third step. We're going to find the height of the third step using the formula we made previously. So again, our first term was 26 because the first step is 26 centimeters tall. And first we have to find the second step. So we're going to go ahead and plug into our formula here to find the second step. We're going to use the first step plus the 26. That's the difference between the two steps. So our second step is 52 centimeters tall. Now we're going to do it again so that we can find the third step. So our second step was 52 centimeters tall. So we're going to use our recursive formula with 26 being the difference. Using 52, we're going to add 26. Now we have found the third step. Okay. This formula, as you can probably tell, is very repetitive, and it would take a really long time to find, say, the 15th step of this pyramid using the recursive formula. The recursive formula you only want to use if you are just finding the third or the second sequence number in the sequence. If you're trying to find something really far away, if you only have 5 numbers in your sequence and you're trying to find the 50th number in the sequence, you do not want to use the recursive formula. So only use this for short consecutive sequences. All right, so now it is your turn. There's some stairs here that are 18 centimeters tall, and they would like you to write the recursive formula to represent the total height of the nth stair. So the next type of formula is called explicit, and we're going to use this formula when we want to find a number that's really far away, like we were just talking about. You use recursive for numbers that are really close in your sequence, but if your number is 100 or 50 or it's really far down the line, we're going to use the explicit formula. The explicit formula is just like the recursive, except we're kind of combining all of our pieces instead of having to do one after another. So the explicit formula for an arithmetic sequence is as follows. It is the first term of the sequence plus the previous term in the sequence times the common difference. All right, so the way that works is as follows. The cost of renting a bicycle is given in the table. How can you represent the rental cost using an explicit formula? So our sequence we're using is the rental cost down here, and you can see that our first term is 26, and our difference between each term is 12. Here is our original equation, our formula. We're going to go ahead and substitute 26 for our first term and substitute 12 for our difference. We are then going to use the distributive property to multiply 12, and we will get 26 plus 12n, take away 12. Then we're going to simplify and combine like terms and do 26 take away 12 to get 14 plus 12n. So the explicit formula for n days, any days that we want to find, is 14 plus 12n. So let's use this formula to actually solve. So we're going to go ahead and figure out the cost of renting a bicycle for 10 days using the formula we made on the previous page. Again, we have our formula here. We're going to find the 10th term. We're going to go ahead and substitute 10 for n. So not only does our little subscript turn into a 10, but our n over here multiplied by 12 is also 10. 12 times 10 is 120, plus 14 is 134. So the 10th term in the sequence is 134, which means it costs $134 to rent a bicycle for 10 days. Okay, so you've learned a lot about recursive and explicit formulas, but we want to go ahead and connect this back to linear functions. The explicit formula of an arithmetic sequence is very similar to a linear function because I can graph the points. It doesn't quite work the same way. There isn't really an initial value. There's a first term, but that's not the same thing as like your y-intercept. But for graphing purposes, you could graph it the same, and the 14, which is your difference, does end up being your initial value. So that's kind of how they're related. You can see here that the function here and the linear equation are the same, and I can graph them just like that, but it's just not quite the same meaning as a normal function. All right, so you're going to go ahead and write an explicit formula yourself. We have the cost to rent a bike is $28 for the first day, plus $2 for each day after that. Write an explicit formula for the rental cost for n days. Then tell me what is the cost of renting the bike for 8 days. Don't forget that in order to write an explicit formula, you need to have the difference between each term and the initial value of the term. So if you need to, go ahead and write out a sequence or a table for each day that you might cost the bike and see if that helps you find those values. All right, we are moving on to page 65 in your student companion, and we're going to go ahead and start to go over how do I take a formula written in explicit form and write it in recursive. So here we have an explicit formula. Sorry, we're doing recursive. This is a recursive formula for the height above the ground of an nth step of the stairs shown. A1, our first term, is 7. So our formula is an take away 1 plus 4, with the first term being 7. We're going to say what explicit formula finds the height. So we're turning the recursive formula into explicit. This is the easier one because they give you the first term and it's easy to find the common difference. So you can just plug it into the explicit formula, and then you do want to multiply this out. Okay, multiply 4 by n and 4 times the negative 1, and then simplify or combine like terms in order to get a final formula. But that's what you do. So if you are given a recursive formula, you can easily turn it into an explicit by just identifying the first term and the common difference and plugging them into the explicit formula. Go ahead and practice that here with these two. Okay, now we're going to go ahead and do the opposite here. This one's a little bit trickier because, as you can see, the explicit formula is simplified. So we have to do a little bit more work to figure out what our difference is. Notice here, though, because I'm going to be distributing that difference, whatever is in front of n is my difference. So identifying the common difference is pretty straightforward. Then I want to find the first term in the sequence, so I'm going to use n as 1, and I simplify. So go ahead and do the last two problems and try it out yourself.